Hi everybody, Mrs. Pesic here. We are looking at the continuation of section 1.7, transformations of functions. So in this section, in the last video, we've already looked at the first two of these learning objectives. We looked at using vertical and horizontal shifts to sketch graphs of functions. We did that part. And we looked at using reflections to sketch graphs of functions. So that leaves this last one that we need to do today, and that's to use non-rigid transformations to sketch graphs of functions. All right, what are non-rigid transformations? Well, first of all, let's make sure we understand what rigid transformations are. Horizontal shifts, vertical shifts, and reflections would all be considered rigid transformations because the basic shape is unchanged. You're just sliding the thing around the graph around the coordinate plane, or you're reflecting it, but really only the position of the graph has changed. All right? But a non-rigid transformation causes a distortion or a change in the shape of the original graph. So let's take a look at this example. So in this case, let's try g of x equaling c times f of x. So let's say we have some parent function f of x, but we're going to multiply that whole function by some constant c. So let's take as our parent function f of x, and let's test out 3 times f of x, so 3 times x squared. So let's see what happens when we try that on our calculator. So in this case, we are going to go to a graphs page, and I would just continue with your 1.7 document that you started when you watched the first part of this video. For this, I'm going to type in my parent function, which is x squared. There's our parent function, and now we want to see what does 3x squared look like. Well, if I push tab and I'm going to type in 3x squared, what happened to the graph? Well, the graph appears narrower than the parent function, but there's really 2 reasons why a graph can appear narrower. It can appear narrower because it's being vertically stretched, or it can appear narrower because it's being horizontally compressed. Vertically stretching something is going to pull it away from the x-axis, but horizontally compressing something is going to be pushing it towards the y-axis. Well, in this case, which is it? Is it a vertical stretch or is it a horizontal compression? And in this case, you can't tell just by looking at the graph which it is, but we can tell by looking at the function, because here's our original function. If we wanted to make like XY chart, for example, let's say x is -1, then the parent, I'm graphing the parent function now, would be +1. If I plug in 0, I get 0, 1 squared is 1, 2 squared is 4, and so on. So that's like my f of x. Let me put f of x here. All right, so this is graphing x versus f of x. But now if I wanted to actually graph this g of x function, that's this one, g of x, then I really need 3 times my f of x. So I need 3 times 1, which is 3. 0 times 1 is still 0. I'm sorry, I'm not doing that right. Let's back up. 3 times 1 is 3. 3 times 0 is 0. 3 times 1 is 3. 3 times 4 is 12, and so on. So what's happening is all of my original y values are now 3 times as high. And if my original y values are 3 times as high, like we're seeing in our graph, then that means that it's been vertically stretched. So this 3x squared here is an example of a vertical stretch of 3. Again, that's because every y coordinate got multiplied by 3. Now, what about if we have 1/2 times x squared? So if we look at that graph, and I'm going to just type in, how does that when I do that? Tab. There we go. So if I do 1/2, I'm doing control divided by 1/2 x squared. So what effect does that have on the graph? Well, now this graph is now wider than the original. And it's wider than the original for one of two reasons. It's either because it's being vertically compressed, like pushed towards the x-axis, or it's being horizontally stretched. And that would be pulling it away from the y-axis. So in this case, this is a vertical compression of 1/2, and I could make another, table, another column in my chart here, but the idea is that this would be a vertical compression of 1/2. All of the y coordinates are only half as high as our original parent function. That's our original parent function, and now we just want half of those heights. All right, so bottom line is, if we have, some function g of x, which is c times a parent function, some number c times parent function. If that c is greater than 1, it's a vertical stretch. If that c is between 0 and 1, then it's a vertical shrink, or we could call it a vertical compression. Another non-rigid transformation happens if we take a parent function like y equals f of x and make a new function out of it, but make a new function by multiplying all of the x's by some constant c. All right, so let's try this and see what happens. We're going to investigate this. Try this on the Inspire, see what is happening. So let's make this our parent function right here. So I'm going to go to my calculator. I'm doing 2 plus x cubed. I need to add a new page to my document, graphs page, and I want 2 plus x cubed, x raised to the third. All right, so there's my parent function. That's what it looks like. And now we're going to do some transformations to it. This time we want to do 2 plus 3x cubed. All right, we're going to try 2 plus 3x cubed. In other words, we're going to where this x is, and instead of the x, we want 3 times x. So we're not multiplying the whole parent function by 3. We're just multiplying the x by 3. So let's see what happens when we do that. I'm pushing tab to get my function line back, and I want 2 plus, and in parentheses, I want 3x raised to the third. So all I did is I'm multiplying all of the x's. Well, I only have one x in this case, but all of our x's are getting multiplied by 3. Well, look at that. This graph looks much narrower than the parent function. But in this case, is this a vertical stretch that's making it look narrower, or a horizontal compression? Is it being pulled away from the x-axis, or is it being pushed towards the y-axis? And in this case, this is a horizontal compression. So let's write that down here. So this is a horizontal, I'm abbreviating, compression. And of, well, we don't want to say a horizontal compression of 3, because that makes it sound like we're doing something 3 times the size. Actually, what we need to do is we need to take the reciprocal of this number here. We need the reciprocal of that number, so it's really a horizontal compression of 1/3. All right, so let's take a look at this example now. This time we are trying 2 plus 0.2x quantity cubed. So this time we're going to take all the x's and multiply by 0.2. So let's see what happens when we try that on our calculator. I'm pushing tab and I'm doing 2 plus, and in parentheses, 0.2x, and that is getting raised to the third power. Well, if you're trying this or you're looking at the screen here, what we see now is a very wide function. Has it been horizontally compressed? I'm sorry, has it been horizontally stretched, or has it been vertically compressed? And this has been horizontally stretched. All right, so in this case, this is a horizontal stretch of, and again, I'm not going to say 0.2, I need to take the reciprocal of 0.2, 1 over 0.2, that's 1 over 2/10. That's 10 over 2. That's 5, so it's a horizontal stretch of 5. So this graph is actually 5 times wider than my parent function was. All right, so that kind of gives you a little outline of our two different types of non-rigid transformations. We've got vertical stretches and compressions, and we have horizontal stretches and compressions. So to sum up the whole idea about the, whoopsie, didn't want to do that. To sum up the whole idea about the horizontal compressions, that happens if you have a parent function f of x, but then you want to make a new function by multiplying every x in that function by some constant. If c is greater than 1, then you're going to have a horizontal shrink or horizontal compression. All right. And for example, if we have this as our parent function, f of x equaling x squared, but then we're going to multiply every x by 2, then this is going to be a horizontal compression of, take the reciprocal of that number, of 1/2. All right. If the c value is between 0 and 1, then we're going to have a horizontal stretch. So again, that's if we plug in a number here, we're multiplying every x value by a number between 0 and 1, then you're going to have a horizontal stretch. So if this was our parent function, f of x equaling x cubed, then our if we have a new function that looks like this, 1/3 x cubed, that's going to look much wider, and that's because this is going to be a horizontal stretch of 3. All right, so hopefully maybe this chart can help us, kind of like a little way to organize our thoughts here. We are going to classify everything in this chart as a vertical stretch, a vertical compression, a horizontal stretch, or a horizontal compression. So in this case, we are starting with a parent function, and let's just use the parent function of, of square root of x. That's going to be our parent function. And in this column here, we are going to see what happens if we multiply the whole function by that constant. And in this column here, we are going to see what happens if we don't multiply the whole function by that constant, but just multiply the x by that constant. All right. So for example, and then we can also take various c values. So here, if we take a c value that's greater than 1, then what's going to happen? We've got an example of 3 times square root of x. That would be a c value greater than 1. All right, and that's if we put that constant out in front of the whole function and that constant is greater than 1, then we're going to get an example like this one right here, okay? And if we have, let's stick with that same theme, but if we have that constant being between 0 and 1, then we've got an example of that, like right here, 1/4 times square root of x. So if the number's outside the whole function, like here and here, these are going to be your vertical stretches and vertical compressions. All right, so erasing this, so I can write, erasing this, erasing this. Okay, so that means that this is a vertical stretch of 3, and this is a vertical compression of 1/4. Before we look at the other things in this chart, let's just test that on our calculator. All right, I'm going to add a new page to my document, as I hope you are as well, and I'm going to put in our parent function, which is square root of x. All right, there's our parent function, and I want to test out the 3 times the square root of x. So I'm going to push tab, and I want 3 times the square root of x. All right, what's happened? That graph has been vertically stretched away from the x-axis, but it's vertically stretched because all of my y values are 3 times as high as they were. So, for example, if 1 went to 1 on the original, now 1 is going to 3. All right. And if let's see, 4 was going to 2, now 4 is going to 6, and so on. So I could plot those points. As a matter of fact, let me just snip this right now so I can write on this. And computer, here we are. Okay, and so let me just pop this in here. So again, the idea is we did have this point, let's say this point right here was 1, 1 on my original graph, but my new point is going to be now 1, 3. All of the y's are going to be 3 times as high because that's what this means. And just to give, well, another example, if I have this ordered pair, whoopsie, this ordered pair, let me move this up. This ordered pair is right here at 4, 2. But if I that's on the parent function, but if I multiply that y coordinate by 3, I would be up here at 4, 6. So all of the y coordinates are 3 times as high. It's been vertically stretched. All right, let me go back to this and let's type in our other function that we looked in our table, and that was 1/4 times the square root of x. So now if I add this graph here, and I'm going to put in a fraction template, control divided by 1/4, and I want x, I'm sorry, not x, I want square root of x. All right, now this graph is much lower than the parent function. It's been vertically compressed because all of these y coordinates are now only 1/4 as high as they were before. So, for example, let me try snipping this one here and popping this back in our document, if it will let me. All right, so here, for example, if I show that I have this ordered pair, my original, on my parent function, nope, that's not my parent function. On my parent function, which is here, this ordered pair was 1, 1. But this ordered pair on my new function, which I guess I kind of lost it, but there's my new function right there. That's the, if I can get it on the screen. Can I get it on the screen? 1/4, there it is. 1/4 times square root of x. This point has now become 1, 1/4. The y coordinate has been multiplied by 1/4. It's only 1/4 as high. Same thing here. My original order pair on the parent function was 4, 2. But this point right here, oops, that's supposed to be a 2. But this point is now 4, 1/4 of 2, which is 4, 1/2. So that's what this order pair is right here. Okay, so back to our notes here. Now let's take a look at what happens when we look at f of x equaling c times x. So if we multiply every x by some constant, what effect does that have? We're going to stick with this same parent function of square root of x, but if the c is greater than 1, we would have, for example, this graph here with square root of 3 times x. But if c is between 0 and 1, we would have, we would have something like this, like square root of 1/4 x. So we're just multiplying the x by a number. We're not multiplying the whole function by a number. So let's investigate this. What happens with this on our calculator? I'm going to add a new page to our document. Control Doc. So I'm adding a new graphs page, and this is going to be square root of x. Oops. All right, that's my parent function. And now I want to try square root of 3 times x. So I'm pushing tab, tab, tab. There we go. And I want square root of 3x. I think that's what we were going for. Yes, it is. And so this graph looks like it's, looks taller. It looks, I guess you'd say, skinnier in a sense, but it's skinnier because it's being horizontally compressed. It's being pushed towards the x-axis. So in this case, I'm going to take another snip of this. A snip of this graph here. And popping it back in here. So what's happening with this? Let's see if we can figure this out. So on this graph, again, I want to picture that I have this starting ordered pair of 1, 1 from my parent function. But instead of saying, oh, what's happening as a change to the y, let's think about what's happening as a change to the x. Like the question really is, what happened? How did the point move over here? I'm having a hard time writing over that graph. But what happened at this point right there? That point is actually 1/3, 1. In other words, if I plug in 1/3 for x, I get 3 times 1/3, that's 1, and the square root of 1 gets me an output of 1. In other words, it's been horizontally compressed, and really I would have to just plug in 1/3 of my x, my original x, to get the same y. That's basically how to think of this. So, let me see if I can do one more example. Let's see, if I had my original ordered pair was 4, 2, that's right here, 4, 2, then what would I need to plug in for x to get 2 on my new function? That's maybe right about here. I don't know, I can't draw very well over that graph. Doesn't like it. But that's supposedly like about the same height of 2, right? I'm trying to grab for 4, 2. And so what would I need to plug in for x to get that same height of 2? Well, I would have to plug in 4/3, right? Because if I take 3 times 4/3, 3 times 4/3 is 4, and square root of 4 is 2. So this ordered pair is actually 4/3, 2. I had to take every x and multiply it by 1/3. So if I take 4 times 1/3, I get 4/3, and so on. So trying to sum up here, this is going to be a horizontal compression of 1/3. And what if we put a 1/4 times the x? Let's go back to our graph, and I'm going to push tab here, and I'm going to do square root of, I put in a fraction template, I need 1/4 x. Okay, now that's looking like it has been horizontally stretched. Now we're pulling it away from the y-axis. So again, here's our original. Come on, original. Doesn't like to move. I'm just going to put that right there. And this is our new graph here. So again, this has been horizontally stretched. Maybe a quick demo of that. And let's see, popping this into our, if I can, go cursor. So again, here, if I compare where my parent function ordered pair was, 1, 1, what would I need to plug in for x to get that same height of 1? Well, 1, 2, 3, 4. I sure think it's going to be right there, because this ordered pair of 1, 1 has now become 4, 1. In other words, what would I need to plug in for x here to get the same output of 1? I would have to plug in a 4 right, for the x to get that same height of 1. So this has been horizontally stretched. Think of it as we're pulling all of these ordered pairs away from the y-axis. So in this case, let's see, going back here, this is a horizontal stretch of 4. All right, so those are just some of my pictures that we were looking at. Okay, so that's it for this lesson. So you're going to have some homework to do, and thanks for watching.